In the YouTube video titled Lecture 9, Modes of Operation for Block Ciphers by Christof Paar, Christof Paar begins by reviewing the previous lecture's discussion of block ciphers. While acknowledging that the simple application scenarios used in the last lectures may be simplistic, he emphasizes that block ciphers possess far more versatile applications than solely encrypting data. He highlights their crucial role in constructing hash functions and message authentication codes, MACs, thereby expanding their utility beyond basic encryption. Paar then introduces the key concept of modes of operation, which are fundamental to effectively employing block ciphers for encrypting large amounts of data. He divides these modes into two categories, deterministic and probabilistic, each characterized by distinct encryption characteristics. Deterministic modes, as their name implies, utilize a fixed and predictable encryption pattern, whereas probabilistic modes introduce an element of randomness and uncertainty into the encryption process. He emphasizes the importance of understanding these fundamental differences as they heavily influence a cipher's security and suitability for diverse applications. Paar then transitions to a more detailed examination of three distinct modes of operation: electronic codebook, ECB, mode, cipher blockchaining, CBC mode, and output feedback, OFB mode. He begins with ECB mode, a simplistic yet vulnerable mode of operation, illustrating how its deterministic nature can be exploited by malicious actors using a straightforward traffic analysis attack. By identifying repeating patterns within encrypted data, an attacker can potentially compromise the confidentiality of sensitive information. To address the vulnerabilities inherent in ECB mode, Paar introduces CBC mode, a more robust approach that incorporates an initial vector, 4, to introduce a layer of randomness into the encryption process. This randomness makes it considerably more difficult for attackers to exploit repeating patterns and compromise the security of encrypted data. However, the selection of the 4 itself becomes a critical factor, demanding careful consideration to ensure its unpredictability and mitigate the possibility of a successful attack. Finally, Paar explores OFB mode, a distinct approach that leverages a block cipher as a pseudo-random number generator, PRNG, to produce a key stream for encryption. This mode proves particularly valuable when dealing with data streams that don't conform to standard block sizes, providing a flexible and efficient encryption solution for non-block aligned data. In conclusion, Christof Paar underscores the significance of thoughtfully selecting the appropriate mode of operation for any given application. He emphasizes that understanding the characteristics, strengths, and weaknesses of each mode is paramount in constructing secure and robust cryptographic systems capable of protecting sensitive information in a constantly evolving digital landscape. From 0 minutes to 5 minutes of the video, Professor Christof Paar commences by situating the audience within the course structure, emphasizing the extensive focus on block ciphers in previous lectures. He underscores the paramount importance of block ciphers as foundational elements within diverse cryptographic applications. Paar goes beyond traditional encryption applications, highlighting their utility in generating random numbers and message authentication codes, MACs. This expansive view of block cipher capabilities lays the groundwork for the lecture's central theme, modes of operation. He then introduces the central topic of the lecture, modes of operation methods for effectively applying block ciphers to messages exceeding the fixed block size. He frames the discussion by contrasting two distinct approaches to encryption, deterministic and probabilistic. Professor Paar elucidates deterministic encryption schemes as methods where the same plaintext, under a specific key, invariably yields the same ciphertext. He highlights the inherent vulnerabilities of such a deterministic approach, particularly in the context of electronic codebook mode, ECB, where identical plaintext blocks produce identical ciphertext blocks. Such predictability renders ECB vulnerable to attacks that exploit readily identifiable patterns within the ciphertext. To mitigate this vulnerability, the lecture then transitions to probabilistic encryption schemes, which introduce an element of unpredictability into the encryption process. This is achieved through the use of an initial vector, 4, a randomly generated value that is added to the plaintext prior to encryption. This injection of randomness ensures that even identical plaintext blocks produce distinct ciphertexts, significantly hindering attacks that rely on pattern recognition. Paar underscores that the selection of a mode of operation is contingent upon the specific cryptographic application and the required security level. He stresses the general superiority of certain modes, like the cipher feedback mode (CFB), in terms of robustness against attacks. The lecture concludes this introductory section by outlining the specific modes that will be examined: ECB, CBC, and CFB, emphasizing the practical importance of these seemingly basic concepts in real-world cryptographic scenarios. From 5 minutes to 10 minutes of the video, Professor Paar delves into the crucial concept of modes of operation for block ciphers, highlighting their essential role beyond basic encryption. He introduces two key classification criteria: deterministic and probabilistic encryption schemes. While deterministic schemes, exemplified by the electronic codebook, ECB, mode, produce identical outputs for identical inputs, probabilistic schemes introduce randomness to enhance security. Professor Paar labels ECB as a terrible choice due to its inherent deterministic nature, which can lead to vulnerabilities like traffic analysis attacks. He vividly illustrates this vulnerability using a real-life scenario involving a bank transfer network. He posits a malicious actor, Oscar, who leverages the ECB's deterministic characteristic to redirect funds to his own account by recognizing and exploiting repeating patterns in the encrypted data. From 10 minutes to 15 minutes of the video, Professor Paar delves into the second key classification criteria for block cipher modes of operation: determinism versus probabilistic. He elucidates that deterministic modes are characterized by their predictable nature, where the same plaintext consistently produces the same ciphertext. Conversely, probabilistic modes introduce a degree of randomness and uncertainty, resulting in distinct ciphertexts for identical plaintexts. Professor Paar then proceeds to examine the electronic codebook, ECB mode, the most basic mode of operation but also one known for its inherent vulnerabilities. He employs a practical example of an electronic funds transfer between two banks, Bank A and Bank B, to illustrate the potential risks associated with ECB mode. In this scenario, a malicious actor, Oscar, can intercept communication on the network, observing repetitive patterns within the encrypted account numbers. This vulnerability arises from ECB mode's independent encryption of each block, leading to identical ciphertexts for duplicated plaintext blocks. Professor Paar emphasizes that Oscar can capitalize on this weakness by rerouting future transfers to his own account. He outlines how Oscar would identify the encrypted account numbers, substitute them with his own, and illicitly redirect funds. The speaker highlights that this attack strategy is a prime example of traffic analysis, where adversaries exploit discernible patterns within encrypted data to extract sensitive information. From 15 minutes to 20 minutes of the video, Christof Paar introduces the electronic codebook, ECB mode, a basic method for applying block ciphers. To illustrate the inherent vulnerabilities of ECB mode, he presents a rudimentary fund transfer protocol. This protocol features a structure where every data field possesses a fixed length of end bits, aligning with the block cipher's block size, e.g., 64 bits for DES. Paar then introduces a hypothetical attacker, Oscar, who exploits the predictable nature of ECB mode to manipulate the fund transfer system. Oscar, with the intention of illicit enrichment, fabricates two fictitious bank accounts, acquiring the required account numbers and bank identifier codes, BLZ, characteristic of German banks. This enables him to surreptitiously intercept and manipulate legitimate financial transactions. Paar elaborates that Oscar identifies specific transfers by recognizing recurring identical ciphertext blocks. For example, he can pinpoint transfers of €1 by observing the consistent repetition of the corresponding ciphertext block. Oscar's ultimate goal is to redirect financial transfers to his own account. He accomplishes this by surreptitiously substituting the authentic account number with his own within the intercepted ciphertext block. However, it is crucial to note that this attack doesn't rely on a chosen plaintext attack, as Oscar doesn't directly exploit the block cipher's weaknesses. Instead, he strategically analyzes the traffic, identifying exploitable patterns in the encrypted data. This attack underscores a fundamental weakness inherent in ECB mode: its susceptibility to traffic analysis. Oscar's successful manipulation of the transfer system is a consequence of the predictable and repetitive nature of ciphertext blocks generated by ECB mode, exposing the system to malicious actors. From 20 minutes to 25 minutes of the video, Christof Paar elaborates on the vulnerabilities inherent in employing the electronic codebook ECB mode for block ciphers. He presents a hypothetical scenario involving a criminal who establishes two bank accounts, one for each financial institution participating in a simulated transaction. Paar highlights that this malicious actor can intercept communications on the banking network and surreptitiously replicate a specific block of encrypted data encompassing a distinctive account number. He then underscores that the criminal can exploit this copied block by substituting the legitimate account number with their own, thereby redirecting funds to their personal account. This illicit maneuver circumvents the security safeguards designed to protect sensitive financial data, enabling the criminal to accrue substantial financial gains. This illicit strategy can be repeatedly executed to siphoning funds from multiple accounts, ultimately generating significant profits for the perpetrator. From 25 minutes to 30 minutes of the video, the speaker introduces the concept of a traffic analysis attack, a technique for exploiting vulnerabilities in the electronic codebook ECB mode of block ciphers. To illustrate this attack, the speaker employs a simplified model of a banking network comprising Bank A and Bank B. The attacker, Oscar, establishes accounts at both banks and engages in eavesdropping on the network traffic to discern patterns within the encrypted data. Oscar observes that each transaction involving the transfer of €1 from his account at Bank A to his account at Bank B consistently exhibits an identical bit pattern. The speaker explains that ECB mode encrypts each block of data independently, rendering the repeating pattern easily detectable in network traffic. Capitalizing on this susceptibility, Oscar can redirect any subsequent transfer intended for Bank B to his own account by surreptitiously substituting his encrypted account number for the intended recipients. The speaker emphasizes that this attack exploits the lack of diffusion inherent in ECB mode. Diffusion refers to the property of a cipher whereby alterations in plaintext significantly alter the corresponding ciphertext. ECB mode lacks this property, leading to identical ciphertext for identical plaintext blocks, a characteristic exploited by the attacker. While this attack might seem implausible or unrealistic, the speaker asserts that it illuminates the inherent vulnerabilities of ECB mode and underscores the imperative for utilizing more robust modes of operation, such as CBC mode, in situations where data confidentiality is paramount. The speaker concludes this section by reiterating the inadequacy of ECB mode for secure encryption in real-world applications where data privacy is a critical concern. From 30 minutes to 35 minutes of the video, the speaker delves into the ramifications of traffic analysis, a technique often employed in adversarial settings to exploit vulnerabilities within a system. He utilizes a hypothetical scenario involving Oscar, a malicious actor who establishes two bank accounts at distinct financial institutions. Oscar then proceeds to execute a series of transfers of €1 between these accounts. Oscar's objective is to surreptitiously monitor the network traffic, leveraging the predictable nature of the electronic codebook ECB mode. The ECB mode, lacking the ability to adequately interweave and obfuscate data, results in identical encryption patterns for every single transfer. This predictable repetition, emanating from the unperturbed 128-bit sequences within each transaction, exposes Oscar's operations to observation. The speaker underscores that this attack strategy does not necessitate cracking the encryption itself, but rather exploits the ECB mode's inherent lack of diffusion. By merely analyzing the traffic flow, Oscar can successfully discern his own transactions, highlighting the critical importance of employing modes of operation that offer robust security and mitigate such easily discernible patterns. The speaker concludes this segment by introducing the concept of wiretapping, or the covert interception of communications, emphasizing the necessity of employing appropriate safeguards to mitigate this threat. From 35 minutes to 40 minutes of the video, the speaker elucidates a hypothetical scenario demonstrating the susceptibility of electronic codebook ECB mode to a man-in-the-middle attack. This scenario features Oscar, a malicious actor, exploiting the deterministic nature of ECB mode to illicitly divert funds. Oscar, having established accounts at both Bank A and Bank B, intercepts the network traffic between the two banks. Due to the deterministic nature of ECB mode, Oscar observes a recurring pattern. Every transfer from Bank A to Bank B utilizes the same encryption key, resulting in identical ciphertexts for identical plaintexts. Oscar exploits this vulnerability by identifying and recording the ciphertext representation of sensitive data, such as account numbers. For example, if BL4 consistently appears as the encrypted account number in numerous transfers, Oscar deduces its plaintext equivalent. Armed with this knowledge, Oscar can redirect legitimate transfers to his own account by substituting the intended recipient's account number with the stored ciphertext, BL4. This attack circumvents the need for knowledge of the plaintext, highlighting the inherent weakness of ECB mode in maintaining confidentiality. The speaker draws a parallel between this attack and frequency analysis techniques used to break substitution ciphers. Just as analyzing letter frequencies in a ciphertext can reveal the plaintext's underlying structure, Oscar exploits the repetition of ciphertexts in ECB mode to identify and manipulate sensitive data. This scenario underscores the critical importance of utilizing secure block cipher modes, such as cipher blockchaining, CBC, which introduce randomness and prevent the predictable encryption patterns exploited in this attack. From 40 minutes to 45 minutes of the video, the speaker elucidates the concept of traffic analysis, a cryptographic attack whereby an adversary intercepts and scrutinizes communication patterns to glean sensitive information without necessarily deciphering the underlying encryption. The speaker employs the scenario of a malicious actor intercepting financial transactions between banks to illustrate this technique. The hacker, recognizing a recurring 58-bit pattern in all transfers from Bank A to Bank B, gains the ability to pinpoint specific encrypted blocks corresponding to those transactions. The speaker posits that the attacker could subsequently redirect future money transfers to their own account, highlighting the susceptibility of the electronic codebook, ECB, mode. He emphasizes that this attack doesn't entail breaking the encryption itself, but exploits the predictable patterns generated by ECB mode, exposing the system to malicious manipulation. The speaker concludes by drawing a parallel between this type of traffic analysis attack and the frequency analysis used to compromise simple substitution ciphers, demonstrating the inherent vulnerability of predictable encryption schemes. From 45 minutes to 50 minutes of the video, the speaker transitions to a comparative analysis of the cipher blockchaining CBC mode and the electronic codebook ECB mode, delving into the vulnerabilities inherent in ECB due to its deterministic nature. The speaker elucidates that CBC, a probabilistic encryption scheme, introduces an element of randomness to the encryption process, thereby ensuring that even identical plaintext blocks result in distinct ciphertext blocks. This randomness is achieved through the incorporation of an initial vector, 4, which, as the speaker explains, can be a randomly generated value or derived from a timestamp or a counter. The 4 acts as a dynamic seed that influences the encryption of each subsequent block. The speaker provides a concrete example. Encrypting the same account number repeatedly using CBC with a unique 4 each time will produce distinct ciphertexts. This characteristic makes CBC a more robust encryption approach compared to ECB, which, owing to its deterministic nature, generates identical ciphertexts for identical plaintext blocks. The speaker underscores the pivotal role of CBC in the realm of modern cryptography, promising a more comprehensive exploration of this concept in subsequent lectures. From 50 minutes to 55 minutes of the video, the speaker embarks on a detailed exposition of probabilistic encryption schemes, emphasizing their departure from deterministic encryption methods. He elucidates that in a probabilistic scheme, identical plaintext inputs, in this case an account number, will yield distinct ciphertext outputs. This contrasts sharply with deterministic schemes where a given input always results in the same output. To illustrate this concept, the speaker employs a practical example drawn from the realm of bank transfers. The process involves encrypting the account number while incorporating a random parameter, termed the initial vector, 4. This 4 functions as a source of unpredictability, ensuring that each encryption of the same account number produces a unique ciphertext. The speaker underscores the critical role of the 4, emphasizing that its reuse constitutes a grave security vulnerability. Repeated use of the same 4 allows attackers to discern patterns and potentially compromise the encryption scheme. Expanding on this concept, the speaker introduces the counter mode, a specific instantiation of a probabilistic encryption scheme. In this mode, the 4 is often a composite value derived from the IP address of the sender and a timestamp, thus creating a unique 4 for every transaction. This rigorous approach enhances the system's robustness against attacks. In conclusion, the speaker forcefully reiterates the paramount importance of using a distinctive 4 for each encryption operation within probabilistic encryption schemes. This underscores the necessity for a meticulous understanding of these principles to ensure the integrity and confidentiality of sensitive data. From 55 minutes to 60 minutes of the video, Professor Paar delves into the fundamental distinction between deterministic and probabilistic encryption schemes. He elucidates that deterministic encryption adheres to a fixed mapping between plaintexts and ciphertexts, rendering the output predictable. In contrast, probabilistic encryption introduces an element of randomness, ensuring that the same plaintext will yield distinct ciphertexts upon each execution. Paar then introduces the counter mode, a mode of operation for block ciphers that leverages a counter mechanism to generate a keystream. The counter, initialized with a specific value such as the recipient's IP address, is increment for each subsequent block. Deciphering is accomplished by generating the same keystream and XORing the keystream bits with the ciphertext. Paar underscores the inherent simplicity of counter mode, emphasizing that the encryption and decryption processes are reversible, with the keystream remaining independent of the plaintext. Despite its absence in introductory cryptography textbooks, Paar stresses the significance of counter mode comprehension for the advancement of cryptographic knowledge. He asserts that it offers a highly practical and efficient means of employing a block cipher in a stream-like manner. The counter mode serves as a quintessential example of how to imbue a block cipher with probabilistic characteristics, even if the underlying cipher itself is deterministic. This demonstration effectively illustrates the implementation of cryptography within real-world scenarios to achieve robust security measures. From 60 minutes to 65 minutes of the video, Professor Paar delves into the counter mode, an alternative approach for encrypting data with a block cipher. This mode employs a counter that advances for each block, rendering the encryption scheme probabilistic. To exemplify this concept, he presents a banking scenario in which Oscar, a criminal, seeks to pilfer funds from 2 separate accounts. Initially, Oscar intercepts and retains an encrypted account number. Subsequently, he establishes a new account and redirects any subsequent financial transfers to this account by substituting the authentic account number with his own, which corresponds to the stored encrypted account number. He accomplishes this by acquiring a block, replacing it with the stored encrypted account number, and subsequently transmitting it back through the network. To illustrate the counter mode's operational mechanics, the professor displays a diagram encompassing the input, encryption procedure, output, and decryption process, emphasizing the congruence of the keystream generation in both encryption and decryption. The professor further elaborates that the counter mode's keystream generation process entails utilizing a counter that increments with each block. For instance, the counter value for the initial block is 000000000. For the subsequent block it becomes 000000001, and so forth. This counter value is then combined with a fixed 4 initial vector to generate a distinct keystream for each block. From 65 minutes to 70 minutes of the video, the speaker delves into the counter mode, a deterministic block cipher mode of operation. Unlike probabilistic modes, counter mode eschews randomness in favor of a systematic approach. A core component of counter mode is the counter, which generates a keystream. This counter is typically 128 bits long and is increment for each block, meaning the second block's counter is 1, the third is 2, and so forth. Notably, the counter's values are not generated sequentially. Instead, the entire set of 128 counter values is generated simultaneously. To bolster security, the counter mode employs a secret initial vector, 4, for the encryption of the first block. The 4 is critical in mitigating potential attacks that could exploit the presence of identical ciphertext blocks. A key characteristic of counter mode is the independence of its keystream from the plaintext. This means the keystream is not contingent on prior ciphertexts or plaintexts. From 70 minutes to 75 minutes of the video, Professor Paar delves deeper into the realm of block cipher modes of operation, specifically focusing on the counter mode. Employing a familiar scenario of a banking network, he underscores the crucial importance of understanding these modes. Professor Paar elucidates how an attacker could exploit vulnerabilities in the electronic codebook, ECB, mode by recognizing repeated ciphertext blocks. This vulnerability allows the attacker to redirect financial transactions to their own account, highlighting the significance of utilizing secure modes such as cipher blockchaining, CBC, mode. Professor Paar subsequently introduces counter mode, CTR, a probabilistic mode of operation that enhances security. He clarifies that CTR mode involves the addition of a random initialization vector, 4, to each plaintext block prior to encryption. This 4, also known as the randomness parameter, introduces unpredictability and bolsters security. Professor Paar further expounds upon the intricate nature of CTR mode, emphasizing that each ciphertext block is intricately dependent on both the corresponding plaintext block and the preceding ciphertext block. This complex relationship renders CTR mode impervious to traffic analysis attacks, solidifying its reputation as a robust and secure mode of operation. From 75 minutes to 80 minutes of the video, the speaker delves into the counter mode, CTR, a mode of operation for block ciphers that operates by XORing each plaintext block with the output of a sequentially increment counter. He illustrates this concept with a scenario where the counter progresses from 0 to 127, yielding 128 unique output bits. A key characteristic of CTR, highlighted by the speaker, is its non-chaining nature. Each plaintext bit is exclusively XORed with the corresponding bit from the counter output, avoiding any interdependence between the bits. This attribute contributes to CTR's simplicity and speed, making it an efficient choice for encryption. However, the speaker emphasizes that CTR lacks the diffusion property present in other chaining modes, meaning the bits are not intricately interwoven to obscure relationships between the plaintext and ciphertext. From 80 minutes to 85 minutes of the video, the speaker transitions to a discussion of the counter mode CTR of block ciphers, a mode of operation that transforms a block cipher into a stream cipher. The speaker highlights that, unlike the previous modes discussed, CTR uses a counter to generate a key stream, which is then XORed with the plaintext to produce the ciphertext. The counter's initial value, known as the initialization vector 4, is agreed upon by both parties, typically a 128-bit value, and is crucial to the security of the system. This 4 is essentially a random value that adds randomness to the encryption process, ensuring that even if the same plaintext is encrypted multiple times, the resulting ciphertext will be different. The speaker emphasizes that the counter is initialized with a value agreed upon by both parties, typically a 128-bit value, and then increment for each subsequent block of plaintext. This results in a deterministic encryption scheme, meaning the same plaintext will always encrypt to the same ciphertext given the same key and 4, while also being considered probabilistic in the sense that different IVs produce distinct ciphertexts. The speaker elaborates on the 4, explaining that it acts as a seed value for the key stream generator and must be kept secret and used only once for a given encryption session. This reinforces the importance of careful 4 selection. The speaker provides a simple example involving a bank transferring €1 from one account to another to illustrate how the 4 can be utilized in a practical context. The initial counter value could be a combination of the sender's IP address and the current timestamp, with the timestamp being precise down to the second or even microsecond level. This further illustrates the importance of the 4 in adding randomness to the encryption process. The speaker concludes the segment by summarizing the counter mode's advantages. It offers a secure and efficient method for encrypting data by employing a counter to generate a randomized key stream that enhances the encryption process. This mode of operation provides a compelling alternative to traditional block cipher modes, particularly when dealing with streaming data. From 85 minutes to 85 minutes of the video, the speaker delves into the counter mode of operation for block ciphers, a technique that leverages a counter to generate a key stream for encryption. The speaker explains that the counter can be implemented in various ways, including utilizing a 32-bit counter and combining it with the recipient's IP address and the time of the day, down to microseconds. Although not entirely realistic, this method serves as a cogent illustration of the concept, demonstrating how a counter can be used to produce a unique key stream for each block. The speaker underscores that the counter is not chained together, meaning that the second bit of the keystream is only XOR'd with the second bit of the plaintext. This independence of the counter allows for decryption by reversing the encryption process using the same keystream generator. The speaker concludes by highlighting the efficiency and simplicity of the counter mode, making it an effective and practical tool for a wide range of applications.